So from the previous discussions, right, for example, from this example, right, we can see that as you superimpose more and more of these complex exponentials on top of each other, you can construct periodic signals that are more and more sophisticated, okay, taking on arbitrary shapes that we like, okay. And in fact, for any signal x of t, you can also find its Fourier series representation with coefficients taken as the inner product between x of t and its corresponding complex exponentials. Now, previously we claimed without proof that any periodic, almost all periodic signals of interest can be written in this form. Okay, so it's of interest to discuss how this convergence occurs, right? So basically, we want to sort of see how this summation, as the number of terms grows to infinity, is able to approximate an arbitrary periodic signal, closer and closer. Okay. So to observe this convergence, we start out by looking at this truncated Fourier series representation. Right? So instead of letting n go to infinity, suppose that we start out by just looking at the superposition of the terms from minus capital N to capital N. Okay? So when you're not summing over all terms, there must be an error between the actual signal x of t and this truncated representation. Okay? And we define the error, we define the energy of the error as the integral of this error squared over one interval. Okay? So we're interested in only one interval because this thing is periodic, right? So it's sufficient to just look at one single interval. Now, suppose that you want to use this truncated Fourier series representation to represent the signal x of t, right? In that case, you would need to find the set of coefficients ak such that this error is as small as possible, okay? Or in other words, you want to find the coefficients ak such that the energy of this error is as small as possible. Now, how do you find the coefficients ak that minimizes this error, okay, the energy of the error? Okay. So a way to do this is just taking the derivative of this with respect to the coefficient ak and setting it to 0. Okay? So because this square term, right, makes this function quadratic, therefore this En, right, this energy, right, if you view it as a function of ak, is minimized when the derivative is 0. Okay? So by taking the derivative of this with respect to the coefficient you're looking for, you can find the optimal coefficient, and it just so happens that the optimal coefficient is exactly equal to this formula that we derived before. Okay? So what this is saying is that even if you just take a finite number of terms, the coefficient that we just derived actually gives you the best approximation of the original function x of t. Okay? So if you want to look into further details of this optimization, you can look into problem 3.66. Okay? Right. Now, this tells you that when you take when you take a finite number of terms, the optimal set of coefficients, AK, is given by this formula here, okay? But what we further want to know is whether or not, or when does the limit of this approximation, okay, truly approximate x of t as capital N goes to infinity, okay? So if we want to say, so if we want to say that this Fourier series representation truly exists for some periodic signal x of t, this means that we hope the limit of the truncated Fourier series representation approaches x of t as capital N goes to infinity. Okay? Okay. So when we ask, like, when does a periodic signal x of t have a Fourier series representation, we're basically asking, when does x of n of t converge to x of t as n goes to infinity? Okay. Now there are different ways to look at this functional convergence. Okay, so there are different ways to look at this. So we won't go into details of these various types of convergence. Okay, if you want to know more about these different types of convergence, you can take a class on mathematical analysis. Okay, but for us, it's just good to know that there are various definitions of these convergence, okay? And different convergence leads to, different definitions of convergence leads to different conditions, right? Now, one notion of convergence is to have this En go to 0 as capital N goes to infinity, okay? And En is basically the integral of the square difference between x of t and xn of t. Okay? So one convergence is to have this go to 0 as capital N goes to infinity. Okay? And this is the so-called L2 convergence. Right? And you can show that L2 convergence holds, okay, for any periodic signal with finite energy over a single period, okay, namely a signal that has an integral, right, where the integral of the absolute square of the signal, is finite over one period. Okay. Now, one thing to note is that even if, right, so if you have a little bit more knowledge about these various types of convergence, right, you should know that, this L2 convergence, right, having the energy of the error go to 0 does not imply that x of n of t is equal to x of t for all t, okay? So this is just one form of convergence, not implying, right? So this does not imply that x of n of t goes to x of t for all t. Okay? So this is a very strict form of convergence, right? This requires the convergence to hold everywhere, right, for all values of t, okay? But for many engineering applications, we do not need such a strict form of convergence, and often this L2 form of convergence is sufficient, Okay. So if you want this convergence, right? If you want this Fourier series representation to hold in terms of this L2 convergence, then it's sufficient to have periodic signals that have finite energy over one period, right? And this includes almost all examples that we will encounter in practice. Okay. Now, another form of convergence is to have convergence at almost all t, right? At almost all values of t except for some isolated points. Okay? In that case, we say we have convergence almost everywhere. So if you want convergence almost everywhere, then one set of conditions is the so-called Dirichlet conditions, which includes three conditions, right? One is for the signal to be absolutely integrable over one period, okay? So absolutely integrable means that the integral over the absolute of x of t is finite over one period, okay? So this is a little bit different from before, right? So from before here, we have the energy, which has a square inside, okay? All right, so condition one is for the signal to be absolutely integrable. Condition two is for it to have, bounded variation, okay? So it should not have, infinite variations within a period. And in that case, this is equivalent to saying that there are only a finite number of maxima and minima within a period. And the third condition is that, also within a period, there can only be a finite number of discontinuities, okay? And each discontinuity has to be finite. So we won't go into the details of why these conditions lead to this almost everywhere convergence, but it's actually not difficult to imagine, because first of all, if you have if the signal is absolutely integrable, then this implies that the coefficient ak, which is less or equal to 1 over t, the absolute of x of t times e to the minus j k omega naught t dt. Okay. So ak originally is the integral of x of t times this, right? So it should be less or equal, the absolute should be less or equal to having this absolute inside the integral. Okay? And this is equal to 1 over t, the absolute integral of x of t, which is finite. Okay. So if the signal is absolutely integrable, this means that all your coefficients are finite. And it's easier to guarantee convergence in this case. Right? If you have coefficients that can potentially be infinite, right, then it's very difficult to prove that the two functions will have vanishing error. Okay? Now here we have a counterexample. Okay, so this is a counterexample. Okay, so a counterexample is having x of t equal to 1 over t within one period. Okay, so in this case, this blows up really fast as t approaches 0. And if you take the integral over 1 over t, it's actually unbounded. Okay. All right. Now the second condition is for x of t to have bounded variations. Okay. And another and counterexample for this is the sine 2 pi over t. Okay. So for this function here, you will see that you have this fast when you do not have bounded variations over one period, this means that it's possible to have higher and higher frequencies as you approach this 0 point for this example. Okay? So in this case, convergence is difficult to obtain because this means that your coefficient ak would be non-vanishing even as k grows up to infinity, right? Because you will have these infinite frequency terms in this signal. Okay? Right. And the same goes for this third condition as well, right? Because for the third condition, you have these infinite number of discontinuities. Okay? So with one discontinuity or a finite number of discontinuities, we can try to aggregate sufficient number of terms to try to approximate a function with a single or finite number of discontinuities. But when we have infinite number of discontinuities, this means, again, that we can potentially have high frequency terms that do not, that are not bounded, okay? Because we have to have more and more of these high frequency terms in order to approximate each one of these discontinuities, okay? All right, but in any case, you can sort of see that all these three conditions do not occur, in most practical signals that we would be interested in. Okay, so no matter which convergence that you're interested in, right, the main message here is that almost all signals of interest would allow us to have a Fourier series representation. Okay? Okay. So here we have this famous example of the convergence towards a periodic square wave. Okay? So here we're trying to use a superposition of these complex exponentials to approximate this square wave here. Now, if you take only one, if you take n equal to 1, meaning that you're taking the three terms k equal to -1, 0, and 1, right, you would get a signal that looks like this. Okay? Now, as you increase n, right, you will get these signals that become closer and closer to the square wave, right? Even though we may see these ripples along the surface, okay? But these ripples become smaller and smaller, okay, as the number of terms increase, right? Now, what's interesting about this is that, when you increase the number of terms in the summation, right, even though the ripples become smaller and smaller, but you continue to observe this overshoot at the edges, okay? And this overshoot, right, the amount of overshoot actually never decreases, right? It actually always remains about 9% above the level, okay? And this is what we call the Gibbs phenomenon. Okay? So when you're trying to approximate a function that is discontinuous, right, using these continuous sine waves, right, you will observe these Gibbs-like phenomenon around the edges. Okay? But this is not a problem because as the number of terms n goes to infinity, this overshoot will go closer and closer to the edge, right? Will become closer and closer to the edge. So eventually, right, closer and closer to the edge. So eventually, for all terms, except for those terms at the point of discontinuity, we will observe convergence. Okay? So this is why, right, in this statement, under Dirichlet conditions, it says that, x of t satisfies its Fourier, is equal to its Fourier series representation, except at isolated points at its discontinuity. Okay, and this is sort of observed from this example here. Okay. Now we can go on to show a few properties of the Fourier series representation. Okay. So these properties include things like linearity, time shifting, time reversal, right, time scaling, multiplication, and so on. Okay? So eventually, you can get a bunch of these properties in this table here. Okay. Now, all these properties you can derive in a straightforward manner. Okay? So let me just do this for a couple of cases. You'll see how this is done, and then you can try to do this for the remaining ones. Okay? All right, so let's start out with linearity. All right. So now we know that for almost all periodic signals of interest, x of t will have a Fourier series representation, okay, with coefficients ak. And we often denote this with x of t, double-sided arrow, ak, with fs on top to represent Fourier series representation. Okay? So this means that x of t has Fourier series coefficients ak, and using Fourier series coefficients ak, you can construct the signal x of t. Okay? So this is a shorthand for the Fourier series representation. Okay. Now what linearity says is that suppose you have two periodic signals x of t and y of t, both periodic with period capital T, and that they have Fourier series coefficients ak and bk respectively. Then if you take a linear combination of x of t and y of t, then the Fourier series coefficient of this superimposed signal will be equal to the same linear combination of their corresponding Fourier series coefficients. Okay? Now, it's straightforward to show this, and we'll do that below, right? So first of all, what this expression says is actually two things, right? First of all, z of t, the superposition of x of t and y of t, should have a Fourier series representation. And secondly, this Fourier series representation is also a superposition of these corresponding ak and bk's. Okay. So for this to have a Fourier series representation, you should first show that the zt is also periodic. Okay. And indeed, because xt and yt are periodic with the same period, therefore when you add them together, zt must also be periodic with the same period. Okay. And you can easily show this, right? Suppose you take zt plus capital T. Right, this is equal to ax t plus capital T plus b y t plus capital T. Okay. And because x and y are periodic, therefore, this is equal to ax of t plus b y of t, which is just z of t. Okay? So hence, we know that z of t is indeed periodic with period t, and therefore has a Fourier series representation. Okay. So in this case, we can write z of t as summation of ck e to the j k omega naught t. Okay. So we can write zt using its Fourier series representation with omega naught that is 2 pi over capital T, right? Because the period is capital T. And the coefficient ck is 1 over t zt e to the minus j k omega naught t dt. Right. So this is integrating over one period. Okay. Now I can substitute this inside. So I get a 1 over t integral x of t e to the minus j k omega naught t dt plus b 1 over t integral y of t e to the minus j k omega naught t dt. Okay? And this integral is the Fourier series coefficient for x of t, which is ak, and this integral is bk. So this is equal to ak plus b bk. Okay, and this shows this statement here. Okay. So the proof for all these other properties are exactly the same. Okay. So for all these other properties, you just directly compute the coefficient of the new transformed function you're looking at, right? And you plug this inside, you will then find the corresponding relationship that you want, okay? So for example, here you would be substituting x of t minus t naught inside here. And for time reversal, you'll substitute x of minus t inside here. Okay, so all of these you can get through direct computation. So tomorrow I won't be able to come to class because I committed to attending an event a long time ago. But in order not to delay our progress, I have posted videos for this chapter. Okay, so when you go back for tomorrow's class, for this part, we're up to 3.5, okay? So for this part, we're up to section 3.5. So for tomorrow's class, please look at the video. Please watch the video up to 3.7, okay? Up to section 3.7. And that will be what we will cover in the midterm next week, okay? So please watch. Up to section 3.7, okay? And this will also be the midterm. Okay, so next Wednesday, I'll try to go through these parts, at least the main points of these parts again, okay? But please still watch the video first, all right? I won't go into details, I'll just talk about the main points. OK？ 有没有什么问题？